So let's take a look at one equation that's already written for us. Consider the skydiver model, where y is a measure of the skydiver's height from the ground t seconds after jumping from the plane. So dy dt equals negative 32t. Suppose a skydiver jumps from the plane at a height of 15,000 feet. Solve and determine how long it takes for the skydiver to drop a total of 1,000 feet. So to do this, let's first take a look at our units of dy dt. So dy dt is no different than what you may have written in an algebra class as delta y delta t. But the difference between these notations is that this could be over a longer period of time. You may want to know how fast the skydiver was falling on average across the entire drop. But this equation tells us instantaneously how fast that skydiver is falling. So dy dt, in all of its glory, has the same units as delta y delta t. And its units are going to be, well, y, the change in y is going to be measured in skydiver's height from the ground. We should have probably said this is going to be in feet. So this is going to be in feet, or change in feet divided by change in seconds. So really, this equation models the speed of the skydiver at any given moment. So let's do a little bit of analysis on this, because we see that dy dt depends on t only. So at time 0, this is basically the skydiver, and here's my fantastic rendition of a plane. We'll have it going this way. There's the wing. Kind of looks like a finger, but hey, good enough, right? So here's the port where the skydiver is going to jump from, and at time 0, the skydiver hasn't jumped from the plane yet. So at time 0, if I plug in 0 for t, negative 32 times 0 is 0. And again, this is feet per second. So before the skydiver jumps from the plane, their altitude isn't changing yet. 1 second later, 1 second after the jump, physics tells us the skydiver should be falling at a rate of 32 feet per second. Now the reason it's negative is because this is the height from the ground, right? So the distance as time passes is going to get shorter and shorter and shorter, etc., as opposed to the distance from the plane, which gradually gets larger and larger. But we are decreasing our height from the ground. So that's the key here. After 2 seconds, wow, the skydiver is falling at a very rapid speed, right? Because this is what we often attribute to the effects of gravity. So, acceleration due to gravity. So there's some acceleration built in here. The way we would solve this equation is we want to basically integrate dy dt, and we know that if dy dt is negative 32t, then what would the function that we started with, I'll call this y of t, that like f of x, but y of t, what function would you have to take the derivative of to end up with negative 32t? Well, I know it's going to have to be a quadratic, because what I'm really asking calculus-wise is what is the integral of negative 32t? And let's see, I'm going to add 1 to the power and divide by that new power. That's going to give me my function, but wait a minute, when I took the derivative of this quadratic function, there could have been an arbitrary constant attached to it. Right? We have to say, when I take the derivative of my y function, do I end up with negative 32t? So this one gives me negative 16t squared plus c. And if I take the derivative of negative 16t squared, I do indeed get negative 32t. If I take the derivative of a constant, then I do get 0. And so we have to have that constant there, because this constant is going to help us satisfy our starting condition, our initial condition. So we have that our function, y of t, is negative 16t squared plus c. Now this is an equivalent but alternative way to think about this. Alternative thinking, this is more of an algebraic way of thinking about solving a differential equation. So if I have an equation, I'm going to get the same answer. This is nothing different. It's just a slightly different way of thinking about it that leads to the same solution. And you're going to find that sometimes shifting your way of thinking can be very helpful. So as long as I do the same thing to both sides of an equation, i.e. integrate with respect to t on the left and the right, then I'm maintaining balance in the equation. So what I'm doing here is just algebra. And on the left, I'm integrating dy dt with respect to t. On the right, I'm integrating negative 32t with respect to t. So I've written this in black just so you can see that I haven't changed the two sides, I've just performed an operation on them. Now what do you do? What do you get when you integrate the derivative of y? Well, if you take the derivative of y and then you integrate it, you get the original function back. And that's one beautiful thing that we know about calculus. If you start with f of x and you take the derivative of that with respect to x, you get f prime of x, or df dx. But then if you integrate it, if you integrate with respect to x, you get your original function back. And this is often a piece of the fundamental theorem of calculus. So if you integrate a derivative, you get your original function back, y. And now if you integrate negative 32t, you get negative 16t squared plus that constant. So notice they lead to the same solution, same result, different ways of thinking. This one's more a little bit more conceptual. This one's a little bit more algebraic. Okay, so now that we've solved it, we have to come back up here and say, well, how am I going to obtain information about the starting value of c? Because I need to answer how long does it take for the skydiver to drop 1,000 feet. So not to get down to 1,000 feet, but we want to know how long will this feet to get, we're starting at 15,000, so we want to ask when is this skydiver going to get to 14,000 feet, and we want to know what's the value of t. So these little diagrams can be very helpful to help you figure out what is it that you're looking for, and then you can develop the tools necessary to get there. So my initial condition, we're going to refer to this as the initial condition, or sometimes you'll see it abbreviated as the IC. Okay? And the way I could write this initial condition is in a couple of different ways. I could say that T naught, Y naught, that this 0 indicates initial, is the ordered pair 0, 15,000. So it just means that when T is 0, Y needs to be 15,000. Another way I could write this is y of 0 equals 15,000, and that's just function notation. So you could write it as an ordered pair, or you could express it as a function. All right, so we're almost there. Let's go ahead and find that value of c. So to find c, we have to solve for our initial condition. Or we have to solve for c by using our initial condition. Y of 0 equals 15,000. So what does that mean? Well, that means I'm going to replace y with 15,000. I'm going to replace t with 0. And I'm going to solve for c. So, of course, this term is 0, and I end up with c equals 15,000. All right. So my final answer is going to be y, or y of t, either way is fine, is negative 16t squared plus 15,000. Okay, now in this, our approach to solving things like when, for what value of t will y be 15,000, we can solve this with a graphing calculator, something like Desmos.com. So let's go ahead and see how we would solve when, for what t, we now need to find for what t is y equal to 14,000. We want to know how long does it take for that skydiver to drop. So I'm going to go ahead and hop over to Desmos and show you how to do this. All right, so here we are in Desmos.com. This is what it looks like, and it's very easy to use. You just click on Start Graphing. There are lots of different features here. You can actually log in. You can share your graph. You can see I'm already logged in here. You can title your graph, so if you want to save it, come back to it later, have it for reference, perfect. There are a few things you can do in here. You can't actually put an image on the graph. Well, I don't think we'll have a need to do that, but you can actually enter a function, you can give yourself some notes, put in a table, put in a folder. Especially if you're going to have a lot of things, having a folder is convenient because what you can do in this folder is you can say add an expression. So what I'm going to plot is, I'm going to call my function f of x. You could just say y equals, but I'm going to use f of x. That way I can show you how to insert a table as well. Negative 16x squared plus 15,000. You're wondering, why am I not using t? Well, if I try to use t, you're going to see that we're going to get a little caution thing over here. And also, nothing really shows up. Oh, I guess it does. Interesting. So probably should stick with x. It's going to ask us to add a slider, so it's x and y are your safe variables. And you can see there's the function. When x is 0, the skydiver is at 15,000 feet. And clearly over here, the skydiver is not going to be falling for more than 30 seconds. And that's free fall. So lots of things that are actually going on in this model here. But over here on the little wrench, you can change things, like you can change the type of grid if you don't want the grid on there, remove minor grid lines, major grid lines, etc. You can have arrows on the axes. You can play around with those things. I'm not really sure what these are to be. Oh, look at that. You can change the way your equation shows up. I know nothing about that, so I will not comment on that at all. So x-axis, well, this is going to be my time. So in here I'm going to put time, t. You can see that that shows up down here. Along my y-axis, I'm going to call this the sky height from the ground in feet. I'll call that variable y. And time down here, I should have said time since jump seconds. So now I can change my x-axis range and go from, say, 0 to, probably don't want to go higher than 32 seconds or 30 seconds, because that's about the time that the skydiver would theoretically hit the ground, although hopefully their parachute would come out. And now we'll go to about, I'm going to go to 15,500. That way I just get the full picture. And now I can zoom out a little bit if I want to, or I can zoom out in and out here as well. If you press the home button, that's going to change you back to your default zoom, the default settings for the graph, so be careful with that if you spend a lot of time doing this. So I want to know, and by the way, by creating this folder, notice that when I put that arrow away, that just makes sure it's all part of one folder, so I could call this skydiver function. Oops. And so that way I know that that's what that folder will contain. You don't have to create folders, it's just convenient. And now I'm going to graph another one. I'm not going to put this one in the folder just because we're not going to be doing a lot of stuff on here. But I want to graph y equals 14,000. And what that means is that these are all the y values where the height of the skydiver is 14,000, anywhere it intersects our blue curve. You don't want to just insert 14,000 because it doesn't really know what that means. You have to say y equals. And the cool thing about this is you see all these little snap points. So if I click and drag with my cursor, you can actually snap to these important points here. Intersections, zeros, vertical, horizontal intercepts, etc. So we see here that it's going to take about 7.9 seconds to reach the height that we are seeking of 14,000 feet. So the skydiver will basically be in the air for about 7.9 seconds. T is about 7.9 seconds. And so just to kind of reproduce that graph that we had here, it looked kind of like this. And this value here was 7.9 comma 14,000. So after you've solved your differential equation, feel free to use Wolfram Alpha, or Desmos in this case, to help you answer those questions about your final function. You could solve this by using quadratic formula or doing some algebra, but honestly, we have bigger fish to fry.